In this video, I want to look at deuterium exchange with benzene. Now, benzene is not a very reactive molecule. It's got a lot of stability, so deuterium exchange with benzene would be a very slow reaction. But if you got some patience, you could see it finally happening. So let's do a DCl. So here's a DCl. How's the reaction going to work? Well, we have those double bonds, and the double bond can slowly attack the DCl. So let's draw out some arrows and kick out the chloride, grab Wolfie's magic arrow, and there's our product. Now, just to remind you, of course, that there obviously was a hydrogen on this carbon to start with, so now there's two hydrogens on that carbon, and here's our positive charge. Well, one of the double bonds has been gone. Now, what are we going to do as a second step? Well, the second step, that chloride is going to come back and react. Now, the chloride could do several things. We could have the chloride come up here and attack the positive charge on the carbon. That would be an addition reaction, but it destroyed the aromaticity, and it turns out that's not a favorable reaction at all. A much more favorable reaction is just to pull off one of the proton and go backwards. Now over here, it could pick on the deuterium and go back just to where we started from, and that happens. And it happened 50% of the time, but it's boring because it doesn't lead anywhere. Much more interesting is to attack the hydrogen, and then have the hydrogen CH electrons come over here and reform the double bond. So that leads us to our exchange. So here's our exchange reaction, where we have just completed everything. We're back to where we started with, except one of the hydrogens on the original benzene is now deuterium. Now, this reaction, I say, is pretty slow. How could we make it faster? Well, one way to make it faster is to stabilize the intermediate species. Because if you stabilize the intermediate, chances are you would also stabilize the transition state leading to that intermediate. How can you stabilize that positive charge? Well, put something on it. Let's say an oxygen, okay, with a methyl, a methoxy. And of course, this oxygen has lone pairs, and that lone pairs can come in and stabilize that positive charge. And what you could do is draw a second resonance structure, okay, the second resonance structure on that positive charge, which would involve bringing in one of the lone pairs like this, okay, and then that resonance structure, if we draw that out, okay, so now we have the positive charge on oxygen. So this methoxy group, okay, could stabilize that positive charge. Now the interesting thing is you could also put a positive charge over in this position, for example, because you could also stabilize the positive charge there. So there's more than one way of doing it, but not every position works. So, but right now we've seen how this works. It stabilizes the positive charge, and of course when the hydrogen has come off here, and now again, if we had our chloride, what would happen when we do our, whoops, that's not an arrow. Here's the arrow. We have our chloride, and now what would happen? And this set of arrows is, I need a chloride. Here's my chloride. And what's going to happen here? Now so the chloride would come, pick off the hydrogen, okay. This bond would move into this position, and this would go there, and we would get our, now with methoxy here. So this would be the complete reaction. I guess I need to draw out the methoxy over here as well. So having that methoxy on there would help stabilize that positive charge by forming this resonance structure will make this reaction go much faster. Now, it's kind of interesting is that the methoxy stabilizes a positive charge, because you might think that the oxygen with its electronegativity would destabilize the positive charge. But it turns out that resonance is much more important than this electronegativity effect. The fact that you can dump the lone pair into a double bond is much more important than any sigma effect, which you'd see by the oxygen withdrawing. Now we can look this at an entirely different way. What I want to do is let me just start over. I'm going to reload the page, go back to my benzene. and but I want to put a methoxy on here. Okay, so here's a methoxy. Okay, and put on the methyl. Now what I'm going to do is I'm going to calculate charges. I'm going to go down here and use the Huckel routine. Turn on the Huckel routine. I do auto select, and I'm going to say show charges. And so now let's look at these charges. This is the Huckel calculations in Oscar is very crude. It's only looking at pi electrons, so it's for example ignoring electronegativity effects, but only pi electrons. And what it's showing is that the oxygen has dumped negative charge into the ring. So the oxygen is now positive, and there's a slight negative charge at the carbon next to this. So if the oxygen is at carbon 1, this is carbon 2, that's negative. Carbon 4 is negative. Carbon 6 is negative. So at the 2, 4, and 6 position, there's a buildup of negative charge from that oxygen. And you can see that if you draw resonance structures, because that's where the negative charge would build up as you put the positive charge on oxygen. So what's happening, that methoxy is in essence making the 2, 4, and 6 positions more basic. Now, of course, we don't call that the 2 position always. We often call it ortho. And the down here at the bottom, we call the 4 position para. So there's 2 ortho positions, 1 para. They're slightly more basic, which means that you'd expect the deuterium exchange to take place faster at those positions. So I hope you follow that argument, and it's not too confusing, but it's a really important concept.